Ask most people in the United States to name the country's most dangerous earthquake fault, and you'll get the same answer almost every time: the San Andreas, running up through California, the fault Hollywood has spent decades turning into disaster movies. But that answer is wrong, and it's wrong in a way that matters enormously for millions of people who have no idea they're living on top of one of the most violent seismic zones in the nation's history. The fault system that produced the most powerful earthquakes ever recorded in the contiguous United States isn't anywhere near California. It sits quietly beneath the middle of the country, threading through Missouri, Arkansas, Tennessee, Kentucky, and Illinois, an area so seismically unremarkable on the surface that most residents drive over it every single day without the faintest idea it's there. It's called the New Madrid Seismic Zone, and roughly 200 years ago it produced a sequence of earthquakes so powerful they rang church bells in Boston, roughly 1,000 miles away, made the Mississippi River temporarily flow backward, and created a lake that still exists today. Today we're going to walk through exactly what happened during that original sequence, why scientists still don't fully understand what's driving earthquakes in the middle of a tectonic plate rather than at its edge, what the newest research published just in the last year is revealing about the mechanics underneath this fault, and why the honest, sober answer to how much danger this region actually faces has almost nothing to do with the fault itself and everything to do with the fact that virtually nobody living above it is prepared. If you find this kind of deep dive valuable, go ahead and hit subscribe and drop a like before we get into it. It genuinely helps content like this reach the people who need to actually understand this risk rather than just react to a scary headline. Let's start with what makes this fault fundamentally different from anything on the West Coast, because that difference is the entire reason this story matters. Every fault most people have heard of, the San Andreas, the Cascadia subduction zone up in the Pacific Northwest, sits directly on the boundary between two tectonic plates, where the Pacific Plate and the North American Plate either grind past each other or one dives beneath the other. That boundary location is exactly why those faults produce earthquakes. The plates are actively pushing, pulling, or sliding against one another right there, and the friction and pressure at that specific junction is what builds toward a rupture. The New Madrid Seismic Zone breaks that entire model. It sits nowhere near a plate boundary. It's buried more than 600 miles from the nearest edge of the North American Plate, deep in the continental interior, in what geologists call an intraplate setting, meaning it's producing a genuinely major earthquakes from the middle of a single, supposedly stable slab of crust rather than at the edge where two plates are actively colliding. That single fact makes New Madrid scientifically strange in a way that few other seismic zones on Earth can match. And it's exactly why researchers have spent decades and are still actively publishing new studies this year, trying to fully explain why earthquakes even happen here at all. To understand where this fault came from, you have to go back roughly 500 million years to a period when the North American continent nearly tore itself apart. A rift began forming through what's now the central Mississippi Valley, an early attempt by the crust to split into two separate landmasses, the same way rifting eventually did succeed in opening the Atlantic Ocean millions of years later. But this particular rift failed. Instead of fully splitting apart, the process stalled, leaving behind a long buried scar in the crust, a zone of weakened, fractured rock sitting underneath what's now southeastern Missouri and the surrounding states, inherited from a tectonic event that happened before complex life had even moved onto land. That ancient scar, called the Reelfoot Rift, is the structural reason earthquakes concentrate here, rather than in the equally distant, equally stable, seeming farmland surrounding it. The rift didn't fully heal over those hundreds of millions of years, and it left the crust in this specific location measurably weaker and more prone to slipping than the solid granite basement rock surrounding it on all sides. Recent geophysical modeling has actually mapped out why that ancient weakness still translates into modern seismicity with such precision, finding that the lower crust directly beneath the New Madrid zone is unusually dense compared to the surrounding region, and that density creates its own gravitational stress, pulling and loading the rock above it in a way that happens to align almost perfectly with the broader regional stress field pushing in from the plate boundaries thousands of miles away. In other words, you've got an ancient structural weak point, and on top of that weak point, the physical density of the rock itself is actively concentrating stress right where the old rift already made the ground more likely to break. That combination, structural inheritance plus modern gravitational loading, is currently the leading explanation for why this specific patch of the Mississippi Valley keeps shaking, while the vast, geologically similar landscape around it in every direction stays quiet. Here's where the story gets even more interesting. Because as recently as this year, researchers have been refining an entirely separate piece of the mechanism, one that doesn't rely purely on ancient rock structure at all. A mechanical model developed by seismologists studying this zone proposes that beneath the weakened upper crust, where the actual earthquakes happen, there's a deeper, warmer, more ductile layer of lower crust that behaves less like solid rock and more like an extremely slow-moving, viscous fluid. When that deep layer gets nudged by some outside tectonic disturbance, it doesn't rupture the way brittle rock does. It slowly relaxes and flows, and as it flows, it gradually transfers accumulated stress upward into the brittle upper crust sitting above it, essentially loading the seismogenic zone from underneath over a period that can stretch across centuries. According to that model, this process can keep generating a whole sequence of large earthquakes, each one triggered as the deep relaxation continues feeding stress upward, until the deep layer finally fully relaxes and the cycle goes quiet again, potentially for 1,000 years or more before it starts building toward the next active period. That framework does something genuinely useful. It explains why the historical record shows large New Madrid earthquakes don't arrive on any kind of clean, predictable schedule, sometimes clustering within a matter of centuries, and sometimes going quiet for stretches approaching 2,000 years because the actual driver isn't a simple, steadily accumulating strain the way it is on a plate boundary fault. It's this much slower, deeper relaxation process working on its own, harder to observe, physical timeline. There's also newer work from just the past year digging directly into how the faults themselves are actually moving, and it's revealed a picture considerably messier than scientists assumed even a decade ago. A detailed study using seismic wave data from actual New Madrid earthquakes to reconstruct the orientation and motion of the underlying faults found that the system isn't behaving the way older models predicted. The Reelfoot Fault specifically, long treated as a single, relatively clean reverse fault where one block of crust rides up and over its neighbor, turns out to actually be sliced through by numerous additional strike-slip faults, breaking it into at least two distinct fault planes where it intersects with another nearby structure called the axial fault. Researchers are now describing the overall stress regime across the zone as transpressive, a combination of compression and lateral shearing happening simultaneously, with real second-order variation in exactly how that stress is oriented from one fault segment to the next. What that ultimately means in plain terms is that the New Madrid Seismic Zone isn't one single, well-behaved fault that ruptures in one predictable style every time. It's a genuinely complicated, interconnected network of smaller fault segments, some behaving like reverse faults, some behaving like strike-slip faults, all embedded in that ancient rift structure, and all still being actively remapped with better instrumentation and better data, even as this video is being made. One more thread of very recent research is worth walking through, because it's honestly one of the more surprising findings to come out of this fault zone in years. Scientists studying the New Madrid area have found that the rate of small background earthquakes there, the constant hum of roughly 200 minor tremors a year that seismic networks pick up but almost nobody feels, actually rises and falls in sync with how much water is sitting in the surrounding landscape. Using satellite gravity measurements that can detect subtle shifts in total water mass across an entire region, combined with local river gauge data and seismic monitoring, researchers found that microseismic activity in the New Madrid zone measurably increases during periods when the Mississippi River basin is carrying an unusually heavy water load, and eases off again as that water drains away, tracking both the normal annual flood cycle and longer multi-year wet and dry periods. The proposed mechanism is that the sheer weight of that additional surface water, spread out over a massive drainage basin, subtly flexes the crust beneath it, and that flexing is just enough to nudge faults already sitting close to their breaking point over the edge into a small rupture. To be completely clear, nobody is suggesting a wet spring on the Mississippi River could trigger a repeat of the largest earthquakes in the region's history. The forces involved in a magnitude 7 event dwarf anything a flood season could contribute. But it's a genuinely elegant demonstration of just how finely balanced and sensitive the stress conditions in this particular patch of crust really are, sensitive enough that something seemingly unrelated as regional flooding shows up as a measurable signal in the earthquake catalog. Now let's actually go back and understand what this fault is capable of when it does produce a major event, because the historical record here is honestly one of the most dramatic in American history, and it doesn't get nearly the attention it deserves. Between December of 1811 and February of 1812, the New Madrid Seismic Zone produced a sequence of at least 3 earthquakes with estimated magnitudes between 7 and 8, an extraordinary release of seismic energy for anywhere in the world, let alone the middle of a tectonic plate. The first massive shock struck in the middle of the night on December 16, 1811, and it wasn't just felt locally. It woke people from their sleep more than 1,000 miles away, rang church bells in Boston, and toppled chimneys as far off as Cincinnati and St. Louis. Thousands of aftershocks followed in the weeks after. A second major shock struck in January, and then the largest of the entire sequence hit on February 7, 1812, an event so powerful it was felt as far away as Quebec in the north and Florida in the south. Eyewitnesses in the region described the ground itself rippling in visible waves, watched massive landslides tear down riverbanks, and reported something that sounds almost impossible until you understand the mechanics behind it, The Mississippi River itself, one of the largest rivers on the continent, briefly appeared to flow backward. That happened because the shaking and associated ground deformation created temporary waterfalls and dammed sections of the riverbed, disrupting the normal flow just long enough for witnesses on the banks to watch the current reverse. The town of New Madrid itself was largely destroyed. Massive sections of riverbank collapsed into the Mississippi. And an entirely new lake, Reelfoot Lake, was created essentially overnight in northwestern Tennessee, when the ground subsided and the Mississippi River poured into the resulting depression. A lake that still exists today and still draws fishermen and tourists with no idea they're looking at a 200-year-old scar left by one of the most powerful earthquake sequences in the nation's history. What makes scientists confident these earthquakes were genuinely as large as the historical accounts suggest, rather than exaggerated frontier storytelling passed down over 2 centuries, comes down to a specific kind of physical evidence buried in the ground itself. Because near-surface faulting is difficult to identify in this part of the country, geologists studying this region rely heavily on something called paleoseismology, essentially forensic geology, digging into the soil to find physical scars left behind by ancient shaking. The most important of those scars are called sand blows, distinctive deposits that form when violent ground shaking causes water, saturated sand deep underground, to liquefy and get forced upward under pressure, venting explosively to the surface the way a geyser vents steam, leaving behind a telltale fan-shaped deposit of sand that can persist in the soil for centuries. Researchers have mapped out extensive fields of these sand blow deposits across the region, layered at different depths corresponding to different earthquake events stretching back thousands of years. And that layered record is how scientists have built out the fault's actual long-term history rather than relying purely on written accounts from the 1800s. That geological record shows the 1811 to 1812 sequence wasn't a one-time freak occurrence. It was simply the most recent entry in a pattern of major, magnitude 7 or larger earthquakes, striking the same zone roughly every 500 to 600 years, stretching back through the prehistoric record. So here's the number that actually matters most for anyone living in this region today, and it's worth being precise about it because vague fear serves nobody. The United States Geological Survey puts the probability of another magnitude 6 or larger earthquake striking the new Madrid Seismic Zone somewhere between 25 and 40% within any 50-year period, a genuinely significant, non-trivial statistical risk. For the truly catastrophic scenario, something approaching the full scale of the 1811 to 1812 sequence, magnitude 7 or larger, the historical recurrence pattern suggests something in that range every 500 to 600 years. And since the last one struck in 1812, we're currently sitting a little over 2 centuries into that interval, which puts the region in the earlier to middle portion of its current statistical cycle, rather than clearly overdue, though the uncertainty band around that estimate is wide enough that a seismologist would tell you honestly that the next major event could be tomorrow or it could be centuries away. The zone continues producing its steady background hum of roughly 200 small earthquakes a year, the vast majority too weak to feel without instruments, occasional magnitude 3 or 4 events that residents do notice. And that ongoing microseismicity is useful confirmation that the fault system remains genuinely active and under stress, even though scientists are quick to point out that all those small earthquakes combined don't meaningfully draw down the accumulated energy that a genuinely major rupture would release. It would take many thousands of magnitude 3 earthquakes just to match the energy contained in a single magnitude 7 event. Now let's talk about why a rupture here would actually be more dangerous, in some very specific ways, than an equivalent earthquake striking California. Because this is genuinely the part of the story that separates New Madrid from every fault most people already worry about. The central and eastern United States sits on older, colder, and far more rigid crust than the fractured, actively deforming rock beneath California. That rigidity sounds like it should be reassuring, but it actually works against the region in a critical way, because rigid, unfractured rock transmits seismic energy far more efficiently across long distances than the broken, heavily faulted rock out west, where numerous small fracture zones absorb and dissipate shaking energy as it travels. A given earthquake in the central United States can be felt clearly across an area roughly 20 times larger than the exact same magnitude earthquake would produce in California, which is precisely why residents 1,000 miles away in Boston felt the ground shake in 1811, a distance that would be almost unimaginable for any West Coast earthquake to reach with comparable intensity. Layer on top of that a second compounding factor, the built environment. Unlike California, where decades of catastrophic earthquakes have forced strict, continuously updated seismic building codes onto virtually all new construction, most of the central Mississippi Valley was never built with earthquake resistance seriously in mind, because for most of the region's development, the risk simply wasn't part of the conversation the way it always has been out west. Memphis, Tennessee, sitting at the southern end of the seismic zone with a metropolitan population of well over 1 million people, is frequently singled out by planners as the single most vulnerable major city in the entire region, built substantially on soft river sediment that amplifies shaking and still home to tens of thousands of unreinforced masonry buildings, older brick structures without steel reinforcement that are exactly the kind of structure known to perform catastrophically when subjected to strong, sustained ground motion. Estimates suggest a repeat of the 1811 to 1812 sequence today could severely damage more than 60% of Memphis's unreinforced masonry stock alone. And despite the existence of retrofit programs in the years since that risk became widely understood, actual compliance remains in the low single digits. The scale of the planning scenarios built around this hazard reflects just how seriously federal and state emergency agencies take it, even if the general public largely doesn't. A joint study led by the Mid-America Earthquake Center, working under contract with FEMA through the Army Corps of Engineers, modeled out the consequences of a magnitude 7.7 New Madrid event striking today across the 8 states considered part of the broader impact zone, and the resulting numbers are staggering. The most cited planning figures point towards somewhere in the neighborhood of 86,000 total casualties, with several thousand of those fatalities, alongside more than 700,000 buildings damaged and roughly 7 million people displaced from their homes across the region. 3 days after the earthquake, in that same modeled scenario, the study projects that over 2 million people would still be seeking temporary shelter, with critical infrastructure severely compromised, including roughly 15 major bridges rendered unusable, directly hampering both search and rescue operations and any large-scale evacuation effort. Direct economic losses across the 8 affected states were estimated at close to $300 billion, with total indirect losses, accounting for the broader disruption to a region that carries a significant share of the country's rail freight, pipeline infrastructure, and river shipping traffic along the Mississippi, potentially reaching twice that figure or more. And there's a specific compounding danger unique to this region that doesn't show up in West Coast planning scenarios at all. If a major New Madrid earthquake struck while the Mississippi or Ohio rivers happen to be running high, which, given how closely tied seismicity here appears to be to regional water loading, is a genuinely realistic possibility rather than a remote coincidence, the shaking could fail levees across the valley, triggering catastrophic flooding layered directly on top of the earthquake damage itself, hitting low-lying communities with 2 simultaneous disasters instead of 1. Given numbers like that, it would be easy to walk away from this feeling like there's nothing anyone in the region can actually do, and that's exactly the wrong conclusion, because unlike the earthquake mechanism itself, which remains a genuinely open scientific question that researchers are still actively refining. Even this year, the response side of this story is squarely within human control. Awareness alone is doing real work here. The same federal and state agencies that produced those sobering casualty figures have also spent years building out the Central United States Earthquake Consortium, a coordinating body linking together the states most exposed to this hazard, running joint exercises, updating regional response plans, and slowly pushing building code improvements into a part of the country that historically never had to think about seismic design the way California has for a century. Retrofit incentive programs targeting the most dangerous unreinforced masonry buildings exist in cities like Memphis, even if participation still lags far behind where officials would like it to be, and that participation gap is itself useful information. It tells you precisely where the most impactful, lowest cost improvements in regional resilience could still be made if awareness of this fault's true history became as widespread in Missouri, Tennessee, and Arkansas as awareness of the San Andreas already is in California. It's worth pausing on that scientific uncertainty a little longer, because not every researcher studying this fault agrees on how much danger it actually still poses. And that open disagreement is itself an important part of the story, rather than something to gloss over. A body of research associated with seismologist Seth Stein has pushed back on the assumption that New Madrid is necessarily building toward another major rupture on anything resembling the historical 500-year clock, raising the alternative possibility that the zone could actually be what he and his collaborators describe as a cooling dying fault system, one where the deep thermal and mechanical processes that powered the 1811 to 1812 sequence are gradually running out of steam rather than steadily recharging toward a repeat performance. That hypothesis rests on measurements of present-day strain accumulation, using GPS geodetic stations planted across the region, some of which have shown surprisingly little detectable ground deformation in the years since monitoring began, a finding that would be genuinely reassuring if it held up, since a fault that isn't measurably straining shouldn't, in the simplest version of earthquake theory, be building toward another large rupture anytime soon. But other researchers studying the same zone have pushed back just as firmly, pointing out that the relaxing lower crust model described earlier predicts exactly this kind of deceptively quiet surface signature. Because in that framework, the actual energy transfer is happening slowly, deep underground, in a way that current geodetic instruments may simply not be sensitive enough to detect until the process is much further along. That unresolved scientific tension, one camp reading the data as reassuring evidence of a dying system, and another camp reading the same data as consistent with a slow, hidden loading process, that conventional monitoring can't yet see, is a genuinely honest reflection of where the science actually stands right now, and it's precisely the kind of open question that makes continued monitoring and continued publication, including the fresh fault, geometry, and stress orientation studies that came out just this year, so important going forward. There's also a geographic wrinkle specific to this region that dramatically shapes how a future rupture would actually play out, and it centers on the city of St. Louis. Unlike Memphis, which sits on deep, soft river sediment that tends to amplify, shaking the way loose gelatin amplifies a vibration compared to solid rock. Downtown St. Louis benefits from a genuine structural advantage, solid bedrock sitting just 10 feet below the surface in much of the urban core. That's an enormous difference from Memphis, where the underlying bedrock doesn't appear until roughly 3,000 feet down, meaning virtually the entire city is built on a thick cushion of soft alluvial soil that shakes far more violently than solid rock would under the exact same earthquake. That single geological fact is a major reason planning scenarios consistently point to Memphis, rather than the larger metropolitan population of St. Louis, as the region's single most vulnerable major city, even though St. Ma. Louis sits closer to the northern reaches of the seismic zone and would still face serious, real damage of its own, particularly to its large stock of older buildings and its extensive underground infrastructure. The Gateway Arch itself, interestingly, was actually engineered with a genuine degree of seismic resilience in mind, but that's very much the exception rather than the rule. Most of the structures surrounding it were built decades before anyone seriously considered earthquake loads as part of standard central United States construction practice. And that mismatch between one carefully engineered landmark and an entire surrounding city of ordinary non-reinforced buildings captures the core vulnerability of this entire region in a single striking image. It also helps to understand that New Madrid isn't some bizarre, one-of-a-kind anomaly on the world stage, even though it can feel that way given how little attention it receives compared to plate boundary faults. Interplate earthquake zones, seismically active regions sitting well away from any tectonic plate edge, show up in a handful of other locations around the planet, including parts of eastern Australia, sections of India far from the Himalayan collision zone, and a scattering of similarly puzzling zones across stable continental interiors in Europe and Asia. Researchers studying those other regions have increasingly converged on similar explanations to the ones driving current New Madrid research. Ancient buried rift structures inherited from failed continental breakups hundreds of millions of years in the past, reactivated by some combination of deep crustal density anomalies, fluid movement percolating up from the mantle, or slow viscous relaxation in the lower crust, feeding stress upward into brittle rock above. That broader pattern matters for two reasons. First, it means New Madrid isn't an isolated scientific curiosity. It's a genuine window into a category of earthquake hazard that shows up in supposedly stable continental interiors worldwide. And lessons learned here have real value for seismologists studying comparable zones on other continents. Second, and more practically, it means the fundamental unpredictability baked into these systems. The wide, centuries-spanning gaps between major events, the difficulty detecting a clear, steadily building strain signal the way scientists can on a plate boundary fault, isn't a shortcoming specific to how well New Madrid has been studied. It appears to be a genuine physical characteristic of how this entire category of earthquake hazard behaves everywhere it occurs. There's a genuinely practical dimension worth spelling out plainly before we close this out, because understanding a hazard this well documented is only half the value. The other half is translating it into something concrete for the millions of people actually living inside this 8-state impact zone. Knowing whether your home or workplace sits on the kind of soft river sediment that amplifies shaking, information that's publicly available through state geological survey offices in Missouri, Tennessee, Arkansas, Kentucky, is worth the relatively small effort of looking it up. Knowing whether a home built before the 1990s has actually been bolted to its foundation, a basic retrofit step that dramatically reduces the chance of a wood frame house sliding completely off its foundation during strong shaking, is a concrete, affordable project rather than an abstract worry. And treating a basic emergency kit, water, food, a battery-powered radio, and a family communication plan for when cell networks inevitably become overwhelmed, as standard household preparation carries the same weight here that it does for any other major natural hazard. The difference being that in this specific region, that kind of preparation remains the exception rather than the norm, which is precisely the gap this video has been trying to close. That gap in awareness is really the whole point of this story, and it's worth sitting with directly. A hazard this well documented, with 2 centuries of eyewitness accounts, thousands of years of paleoseismic evidence buried in the soil, and an entire body of active, cutting-edge research still being published this year on the exact mechanics driving it, isn't a mystery in the way a genuinely unpredictable disaster would be. Scientists can tell you with real confidence how the last major sequence unfolded, what geological structure is concentrating stress beneath the region, roughly how often events of this scale have repeated throughout the deep past, and precisely which cities, which building types, and which pieces of infrastructure carry the highest risk when the next one arrives. What's genuinely missing isn't scientific understanding. It's the same kind of decades-long, sustained public seriousness that transformed California from a state full of vulnerable, unreinforced buildings into one of the most earthquake-prepared regions on the planet. New Madrid doesn't need a scarier headline. It needs the version of California's multi-decade earthquake culture, transplanted into a part of the country that has never quite believed it needed one. Closing that gap doesn't happen because of a single dramatic video or a single frightening statistic. It happens the same slow way any region builds genuine resilience, through updated codes, funded retrofits, practiced drills, and a public that understands its own ground well enough to actually prepare for what the geology has already shown it is fully capable of doing again. If you found this breakdown genuinely useful, drop a comment and let us know if you live anywhere in this 8-state region and whether you'd ever actually heard of the new Madrid Seismic Zone before today. Because the gap between how well documented this fault is scientifically and how little it's actually discussed publicly compared to California is honestly one of the strangest imbalances in American disaster awareness. Share this with anyone you know living in Missouri, Arkansas, Tennessee, Kentucky, or the surrounding states. Because a huge number of people in this exact region genuinely have no idea they're living directly above one of the most historically violent fault systems in the country. And if you want to keep following how this research develops alongside everything else shifting across the country's most closely watched seismic hazards, subscribe and turn on notifications so the next update reaches you the moment new data comes out. Thanks for sticking with this one all the way through. We'll keep tracking every new study on this fault's deep mechanics, every shift in regional preparedness efforts, and every fresh piece of the puzzle as researchers continue working to understand exactly why the middle of a tectonic plate keeps producing some of the most powerful earthquakes in American history.